Hello everyone, welcome to my channel, and today we'll be starting Electrostatics, the class 12 physics first chapter. Okay, so in this chapter basically we'll be covering the introduction of electrostatics, the electric charge, the conduction and induction, the conductor and insulator, charging of a body, Coulomb's law, and the questions. Okay, so we start here. Now, what is electrostatics? Electro means electric, right? And statics means rest. So, electrostatics is a branch of physics that studies electric charges at rest. Since classical physics, it has been known that some materials, such as amber, attract lightweight particles after rubbing. The Greek word for amber or electron was thus the source of word electricity. So here we get our point. Electrostatics is the branch of physics that studies electric charges at rest, right? So electrostatics is the study of electric charges at rest. Now, when we comb our hair on a dry day and bring the comb close to the tiny pieces of paper, we note that they are swiftly attracted by the comb. When we just put some paper, when we take some paper, okay, we took some paper. So on a dry day, when we take a comb, we normally we took a comb, and here are some tiny pieces of paper. Okay, so when we'll be bringing the comb close to here, we'll see that there is nothing happening. But once you comb your hair with the comb, and then you bring that here, then you'll see that the papers are getting attracted to the comb, right? So we see that the comb, after rubbing the hair, it becomes charged and it's attracting the papers. But when it was uncharged, then it showed nothing. So here it said that the similar phenomena occur if we rub a glass rod or an amber rod with a cloth or with a piece of fur. Why does this happen? What really happens in electric circuit? How do electric motors and generators work? The answers to all these questions come from a branch of physics known as electromagnetism, the study of electric and magnetic interactions. These interactions involve particles that have a property called electric charge, an inherent property of matter that is a fundamental as mass. Now we come to the point atom. Now in atom, what do we have? We have electron, neutron and proton. Electrons revolve in their orbits, right? And in the nucleus, we have a neutron and proton. Now the mass of proton is 1.673 into 10 to the power minus 27 kg, and the neutron's mass is slightly more than proton. It is 1.675 into 10 to the power minus 27, and the mass of electron is 9.11 into 9.11 into 10 to the power minus 31 kg. All right, and the electron. Now if you would ask me what is the charge of electron, proton, neutron, then I would say this, that electron has a negative charge, right? Electron, it has a negative charge. Proton has a positive charge because it is in the proton, so proton will have a positive charge and electron will have the negative charge, and neutron has no charge. Now please be really careful with this, it has no charge, right? So we'll only be studying the electrons and the protons because neutrons has no charge, we cannot charge it. So electron is negatively charged, proton is positively charged. Okay, now we come electric charge. The electrical nature of matter is inherent in atomic structure. An atom consists of small, relatively massive nucleus that contains particles called protons and neutrons. A proton has a mass 6.73 into 10 to the power minus 27 kg, while a neutron has a slightly greater mass, 1.675 into 10 to the power 27 kg. Surrounding the nucleus is a diffused cloud of orbiting particles called electrons. An electron has a mass of 9.11 into 10 to the power minus 31 kg. The PDF, the written thing, we will be finding the PDF in the description box, so you can go and see it. Like mass, electric charge is an in intrinsic property of protons and electrons, and only two types of charges have been discovered. I have said here that we'll be discussing in only these negative and positive, because we have no charge in electrons. Okay, so a proton has not been discovered positive, and it's just only two charges have been discovered, positive and negative, till now. So we have that a proton has a positive charge and electron has a negative charge. As I said here, that the electron will have the negative charge electron, and the proton will have the positive charge, and neutron will have a no net charge. Okay, so we have that a proton has a positive charge and an electron has a negative charge. A neutron has no net electric charge. The magnitude of the charge on the proton exactly equals to the magnitude of the charge on the electron. The magnitude of the charge of the proton and electron is just same. Only in the proton we will have a positive charge, and in electron we will have a negative charge. Okay, the proton carries a charge plus E and an electron carries a charge minus E. The SI unit of charge is Coulomb. C and E has the value E equal to 1.6 into 10 to the power minus 19 Coulomb. Okay, in when it will be proton, then we'll be using plus positive. When it's electron, we'll be having negative, but the magnitude of proton and electron is same, 1.6 into 10 to the power minus 19 Coulomb. Okay, regarding charge, the following points are worth noting. Like charges repel each other, and unlike charges attract each other. When it will be like charges, it will repel, right? And when it's opposite charges, it will attract. Okay, so here we have, so the like charges it's repelling, and the unlike charges are attracting. Charge is a scalar quantity and can be of two types, positive or negative. Now please be very careful. It is written charge is a scalar quantity. If you will be getting a question that charge is having a positive and negative, and just tell me that if it's scalar or vector, then you might say that it's a vector because it's having positive or negative, but no, it's a scalar quantity, and it has two types, positive or negative. Negative it will be when it's electron, and positive will be when it's proton. Charge is quantized. The quantum of charge is E. The charge on any body will be some integral multiple of E. That is Q equal to plus minus NE, where N is 1, can be 1, 2, 3, any number. Okay, and Q is the charge, and E is 1.6 into 10 to the power minus 19 Coulomb. Okay, charge on any body can never be 1 by 3 E 1.5 E. It cannot happen like this. Okay, now there is a note, apart from charge, energy, angular momentum and mass are also quantized. Apart from charge, energy, angular momentum and mass are also quantized. The quantum of energy is hv, the sunlight hv, and that of angular momentum is h by 2 pi. Okay, quantum of mass is not known till date. Okay, quantum of mass is not known till date, but the quantum energy is hv, and that of the angular momentum is h by 2 pi. Okay, hv and the angular momentum is h by 2 pi. The proton and neutrons are combination of other entitles called quarks, which have charges plus minus 1 by 3e and plus minus 2 by 3e. However, isolated quarks have not been observed, so quantum of charge is still E. Okay, now the fourth point. During any process, the net electric charge of an isolated system remains constant, or we can say that the charge is conserved. Okay, the charge is conserved. The net electric charge of an isolated system remains constant, or the charge is conserved in the isolated system. Pair production and pair annihilation are two examples of conservation of charge. The pair production and pair annihilation. A charged particle at rest produces electric field. a charged particle in an unaccelerated motion produces both electric and magnetic field. Now, a charged particle at rest, okay, it's not moving, produces electric field, and a charged particle which is moving, which is not accelerating, which is moving, produces both electric and magnetic fields. Okay, both electric and magnetic fields, but does not radiate energy. They don't radiate energy. Okay, but an accelerated charged particle not only produces an electric and magnetic field but also radiates energy in form of electromagnetic waves. Now you'll be now just look at here. When it's rest, okay, when a charged particle is at rest, it produces electric field and it does not radiate energy. 2 points we get here. Okay, the 2 points is when it is at rest, it produces electric field only, and when it is and so when the charged particle is at rest, it will produce electric field only, and it will not radiate energy. When it is unaccelerated, okay, the charge is an unaccelerated motion, it will produce both electric and magnetic fields, and it will radiate energy in form of electromagnetic waves. Clear? Again repeat. In rest, no, it only produces electric field and no radiation. Okay, does not radiate energy. When it's unaccelerated, when the electric charge is in an unaccelerated motion, it produces both electric and magnetic fields, and it radiates energy in form of electromagnetic waves. We have a question here. How many electrons are there in 1 coulomb of negative charge? So the negative charge is due to the presence of excess electrons, right? If we have excess protons, then we have their positive charge. We have excess of electrons, we have a negative charge. Since they carry negative charge, because an electron has a charge whose magnitude is 1.6 into 10 to the power minus 19 coulomb. Look here. Okay, so memorize this. Okay, so we have the number of electron is equal to the charge q. What was the formula of q? Q equal to plus minus Ne divided by the charge E on each electron. Therefore the number of, we need to take out the n of electrons. So n equal to q by E. We just bring this E here, right? So q equal to plus minus E. So you need to memorize, for now you need to memorize these two. E equal to 1.6 into 10 to the power minus 19 coulomb, and Q equal to N into E, where N can be any integral number 1, 2, 3, and E is the electric charge. Okay, it's the electric charge, and Q is the charge. Okay, so here we got N equal to Q by E, and we got the answer 6.25 into 10 to the power 18. Okay. Now, what is conduction? Conduction is the process by which heat energy is transmitted through collisions between neighboring atoms or molecules. Conduction occurs more readily in solids and liquids, where the particles are closer to together than in gases, where particles are further apart. Conduction is the phenomenon of transfer of heat through one part of the body to another, from particle to particle, in the direction of fall of temperature without any actual movement of the particles. Here we have the conduction in contact. Okay, and induction is defined as current production in the coil due to change in magnetic flux in itself or another coil. There will be change in itself or in there will be change in the magnetic flux in the coil itself, because which a current will be induced in itself. So conduction is in contact and the induction is this. So now we have conductors and insulators. For the purpose of electrostatic theory, all substances can be divided into two main groups: conductors and insulators. In conductors, the electric charges are free to move from one place to another, whereas in insulators they are tightly bound to their respective atoms. So we know that the conductors conduct. Okay, so the electrons are really like, it's not tightly bound. But insulators, it do not conduct, so it just pulls all of his electrons to himself, right? So conductors are whose electric charges are free to move from one place to another, and insulators, they are tightly bound. Okay, in an uncharged body, there are equal number of positive and negative charges. A body which is uncharged, okay, we have equal number of positive and negative charge. The examples of conductor of electricity are metals, human body, the earth. The example of insulator are glass, hard rubber, and plastics. In metals, the free charges are free electrons known as conduction electrons. Okay, in metals, the free charges are free electrons, which we say conduction electrons, the electrons which will conduct. Okay, in insulator they are bound, they don't conduct, and in conductors the electrons are free to move. So these free electrons, we can also say that conduction electrons. Semiconductors are a third class of materials, and their electric properties are somewhere between those of insulators and conductors. Silicon and germanium are well known examples of semiconductor. Silicon and germanium are the group 14 elements of p block in carbon family. Okay, I think you remember this, it was in class 11's chemistry. So this was in conductors and insulator. I again repeat my point. In conductors, the electric charges, the electrons are free to move. Okay, it conducts electricity. And in insulators, the electrons are tightly bound and they don't conduct. So the examples of conductors are metals, human body, and the earth. And the example of insulator are glass, rubber, hard rubber, and plastic. So now we come to the point of charging a body. Mainly there are following three methods of charging a body. The first method is charging by rubbing. Now when we rub our like here I said, when we'll be rubbing the comb with our hair, then this comb will be getting electrically, it will get electrically charged, and it will attract these tiny pieces of paper. Okay, so the charging by rubbing, the simplest way to experience electric charges is to rub certain bodies against each other. When a glass rod is rubbed with a silk cloth, the glass rod acquires some positive charge and the silk cloth acquires negative charge. Okay, the glass rod will have a positive charge and the silk cloth will have a negative charge. So positive and negative will attract the unlike charges by the same amount, okay. So the positive and the negative will be attracting and they'll be in the same amount. The explanation of appearance of electric charge on rubbing is simple. All material bodies contain large number of electrons and equal number of protons in their normal state. As I said that if a body is uncharged, then it will have equal number of positive and negative charges. When rubbed against each other, some electrons from one body pass on to the other body. The body that donates the electrons and become positively charged, while the which receives the electron becomes negatively charged. The one who is giving the electrons, they are positive. The one who is taking the electrons are negative. Okay, for example, when glass rod is rubbed with silk cloth, glass rod becomes positively charged because it donates the electrons. And while silk cloth becomes negatively charged because it receives electron. Electricity is so obtained by rubbing two objects is known as the frictional electricity. The other places where the frictional electricity can be observed are amber is rubbed with the wool or a comb is passed through a dry hair cloud also become charged by friction. So charging by friction is frictional electricity. Static or frictional electricity is a type of electricity that is produced whenever these two suitable substances like hair and comb, glass and rod and silk, sealing wax and wool are rubbed together vigorously. Okay, vigorously the friction over each other to develop a charge which is small in magnitude. It is also known as triboelectricity or the frictional electricity. Charging means gaining or losing electron. Matters can be charged in some ways, charging by contact or charging by induction. Charging by contact. Charging by conduction engage the contact of a charged object to a neutral object. It is positively charged aluminium plate is touched to a neutral metal sphere. The neutral metal sphere, in contrast to induction, where the charged object is brought near but never contacted to the object being, conduction charging makes the physical connection of the charged object to the neutral object. Since charging by induction involves contact, it is often called charging by contact. Here we took two bodies, one is charged and one is neutral, and when we bring them in contact, we'll be seeing that this charged body will make this neutral body charged too. And this charge, which like charging a body, bringing it in contact, is called charging by contact. The charged body comes near the neutral body in contact and they get charged. Okay. Principles of charging by contact. When charged object contacts to a neutral object, they both have some charge. When charged object contacts to a neutral object, they both have the same charge. The charged object contacts to a neutral object, they have both same charge. When two charged matter contact each other, total charge of the system is preserved and they distribute the total charge in accordance with their capacities. Okay, these are the some points, the principles of charging by contact. So when charge object contacts to a neutral body, they both have the same charge. Okay, both have same charge. When two charged matters contact each other, the total charge of the system is preserved and they distribute the total charge in accordance with their capacities. If touching objects are spheres, they contribute the total charge according to their radii, because the capacities are directly proportional to their radius. Please be careful with this point. The capacities are directly proportional to the radius. So more the radius, more is the capacity. Less the radius, less is the capacity. When the spheres are same, they share total charge equally. Okay, when the spheres are same, they share total charge equally. Charging by induction. Induction charging is a method used to charge an object without touching the object to any other charged object. So charging by contact, okay, bringing the charged body in contact with the neutral body, right? And charging by induction is without touching, without bringing it in contact, charging the body. Now we come to the point, Coulomb's law. The law that describes how charges interact with one another was discovered by Charles Augustin de Coulomb in 1785. With a sensitive torsion balance, Coulomb measured the electric force between charged spheres. It measured the electric force between charged spheres. In Coulomb's experiment, the charged spheres were much smaller than the distance between them, so that the charges could be treated as point charges. The results of the experiments of Coulomb and the others summarized in Coulomb's law. The electric force Fe exerted by one point charge on another acts along the line between the charges. It varies inversely as the square of the distance separating the charges is proportional to the product of charges. The force is repulsive if the charges have the same signs, and attractive if the charges have opposite signs. The same thing, if like they're like charges, it will repel. The unlike charges, it will attract. The magnitude of the electric force exerted by the charge q on another charge q2, q1 and q2, a distance of r. So as here we got a point that radius is inversely proportional to the force, right? So radius is increasing, force will decrease. Radius is decreasing, the force will increase. Okay, so Fe is equal to k. K is a constant. Q1, the q1 charge and the q2 charge, and the distance, okay, r square. Now the value of the proportionality of the constant k in Coulomb's law depends on the system of units. Constant k is Coulomb law depends on the system of units. It in SI unit, the contact k is k equal to 8.988. It is almost equal to 8.988 into 10 to the power 9 Newton per meter square by Coulomb square. Okay, then we have the value of k is known to such a large number of significant digits because this value is closely related to the speed of light in vacuum. This speed is defined to be exactly 2.99792,458 into 10 to the power 8 meter per second. It seems like a phone number, right? Okay, so 2.99792 458 into 10 to the power 8 meter per second. The numerical value of k is defined in terms of c to be precisely k equal to 10 to the power minus 7 ns square by c square small c square. Okay, so 10 to the power minus 7. This you need to memorize. Okay, this constant k is often written as 1 by 4 pi epsilon naught. Okay, so here we can write this. Okay, substituting the value of c, we get these are the things in example of problems we will often see. Now in the while solving the problems we'll be using the value of k as 9.0 into 10 to the power minus 9 or somewhere 1 by 4 pi epsilon naught. Okay, now here the quantity of epsilon naught is called permittivity of free charge. It has the value e epsilon naught is equal to 8.854 into 10 to the power minus 12 coulomb square newton per meter square. So the quantity epsilon naught is called the permittivity of free space. Okay, the permittivity of free space. These are some points you need to like keep it in your head, like the things which I've highlighted. So epsilon naught is 8.854 into 10 to the power minus 12 coulomb square newton per meter square. Okay. Regarding Coulomb's law, the following points are worth noting. Coulomb stated above describes the interaction of the 2 point charges. When two charges exert forces simultaneously on a third charge, the total force acting on that charge is a vector sum of forces. Okay, like suppose here it's of F1 and this is F2. So we'll be taking out the resultant, right? So the vector sum of addition, so F net will be the f1 square plus f2 square plus 2 f1 f2 cos theta. Alright, now so here it is the sum of the forces. This important property called the principle of superposition of forces holds for any number. Thus f net can be f1 plus f2 plus f3 till fn. Okay, so I again repeat, in Coulomb stated above describes the interaction of two charges. The two charges exert forces simultaneously on the third charge. The total force acting on that charge is the vector sum of forces that two charges would exert individually. This important property is called principle of superposition of forces holds for any number of charges. Thus f net equal to f1 plus f2 plus f3 plus f4 till n. The electric force is an action reaction pair, that is two charges exert equal and opposite forces on each other. Okay, the action and reaction pair. Okay, so the two charges exert equal and opposite forces on each other. These are the points you need to keep in your mind. The electric force is an conservative in nature. Okay, so the electric force is conservative in nature. These are the points you really, if you will keep in mind, it will really help you if any questions come, like basic questions or the theory questions which you get. Coulomb's law, as we stated above, can be used for the point charges in vacuum. If some dielectric is present in the space between the charges, the net force acting on each charge is altered because charges are induced in the molecules of inverting medium. The force decreases k times if the medium extends till infinity. Here k is dimensionless constant which depends on the medium called dielectric constant of the medium. Thus F equal to 1 by 4 epsilon naught q1 q2 by r square. Okay, and here if we'll be seeing the F net, so here the epsilon naught into r is the permittivity of the medium. Okay, now extra points to remember. A few problems of electrostatics. Lam's theorem is very useful. According to this theorem, if three concurrent forces F1, F2 and F3 is equal to 0, then we can also write F1 sine alpha by F2 sine beta by F3 sine gamma. They are equal. Okay, like this. Suppose the position of vectors of two charges q1 and q2 are r1 and r2. Then electric forces on the charge q1 due to the charge q2 is F1 1 by 4 epsilon naught. This is k. Okay, k q1 q2 and r1 minus r2 whole, it is the power 3, and r1 by minus r2. Similarly, electric force on charge q2, it will be the same. So here q1 and q2 are to be substituted with the sign r1 x1 i cap, y1 j cap, and z1 k cap, and r2 x2 i cap, y2 j cap, and z2 k cap, where x1 y1 k1 and x2 y2 k2 are the coordinates of the charges q1 and q2. Now we takes a question: what is the smallest electric force between two charges placed in the distance of 1 meter? So the smallest electric force between the two charges, we know the formula F equal to k q1 q2 by r2 r square. So here r is 1 meter. All right, so we'll be taking out, so we get the k's value 9.10 to the power 9. I said you to remember this. Look, here we have k equal to 9.0 into 10 to the power 9 minus 9 by 9.0 into 10 to the power 9, or 1 by 4 epsilon naught. Okay, so we'll be putting the values. This is the E, the charge E, right? Okay, so we get the answer 2.304 into 10 to the power minus 28 Newton. It was really a simple question. We just need to put up the values in the formula and we'll be getting the answer. Okay, now we take a really good question. Three charges q1, q2 and q3 are placed on the vertices of an equilateral triangle of side 1 meter. Find the net electric force acting on the charge q1. There are two methods. Okay, this is the method 1 and here we have the method 2. So in the figure we draw the f1, f2 and f net, and we'll be taking out the f net. So in the figure f1, the magnitude we took out, just putting the values. All right, we put up the values and then we got the f1. Okay, f2 q2 q1. Okay, and then we'll be taking out the f2 q1 into q3. f1 we had q2 and q1. In f2 we'll have q1 and q3. So the q3's value we'll be putting up here, right? 3.1 3.0 into 10 to the power minus 6, 1.0 into 10 to the power minus 6, and the value of k, which is 9.1 into 10 to the power 9 here. Remember? Okay, so we took out the f2 similarly, and then we take out the f net. So we take out the f net, which is f1 square plus f2 square, to the formula we had a square plus b square plus 2ab cos theta. Okay, so we take out here, and the tan alpha, the formula a sine theta by b a sine cos theta. All right, so we got the alpha as 79.2 degree. Thus the net force, we took out the net force, the vector sum of addition. Okay, remember, so the net force on the charge q1 is 2.38 into 10 to the power minus 2 Newton, and the angle is alpha equal to 79.2 with a line joining q1 and q2 as shown in the figure. Now we have method 2. In this method, let us assume a coordinate axis with q1 at origin as shown in the figure. The coordinates of q1 and q2 and q3 in this coordinate system are 0, 0, 0, 1 meter dx and so on. So we take out the f1. Okay, same thing in we'll be taking out in the coordinates. So we got the f1, we take out the the net force is on q, f equal to f1 plus f2. Once So we'll be simply taking out the F1, F2, and we'll be adding up and we'll get the sum of forces. Okay. Once you write a vector in terms of I, j cap, there is no need of writing the magnitude and the direction of the vectors. Alright. So we'll see that the way we were solving the projectile motion in two ways. Either we'll be taking the three formulas of the kinematics and we'll be solving it, and then we take the coordinates thing. The same way it's here. Either I solve it in the vector sum of addition or in the taking the coordinates. Okay, so we covered our part 1 and we'll be soon taking out the part 2 and part 3 of the electrostatics. Basically in electrostatic there are 15 topics. Okay, like this we have 15 topics, so I'll be covering up 5 topics in one video. Okay, so we'll be having part 3 of electrostatics, so part 2 will be going to come soon, so please stay tuned. And the part 1 we covered introduction, the electric charge, the conduction and induction, conductors and insulators, charging of a body, the three types of charging: charging by rubbing, charging by contact, charging by insulators, Coulomb's law, Fe equal to K mod Q1 Q2 by R square. And then we solved the questions. So I thank you for watching my video. See you with the next video. Thanks for watching.